Let's open your textbooks, Cylindrical textbooks. Problem 6.15. Page 276. Okay. All right. So if you see to the questions, look at the questions, you are given a cylindrical capacitor again. So now we are always playing with capacitor. So anything you see two conducting surface, operate, and there is an insulator or dielectric in between, that's called capacitor. So same thing goes to this case. So you are given a cylindrical capacitor. Let me draw here. So you have inner or internal surface with the radius of A, and then we have the outer conducting surface, let's say with the radius of B, right? So the B and A. The A, we know that the value of A given as 5 mm, and the value of B is given as 15 mm. So to make it easy, so make sure your derivations using variable. So if you put value, also okay, but sometimes become not really nice. Okay, so just use variable A, B, so it's much more convenient or much more simple. All right, so also this case for the outer conducting surface is grounded. It means that at this surface we have zero potential. And then for the inner surface here is connected to the 100-volt here. Okay, that's the boundary condition given to us right now. Again, for this case, do we have any rho v given in the equation? I don't think so. So you see the inner and outer radius as such, and V at 5 to 100, and V at 15 to 0 volt, and calculate E, V, and V. So, and rho S on each plate. All right, guys. Yes. So again, this case we are not given any rho v, so straight away you can assume the rho v is 0. It's like a free charge medium. So again, we can use Laplace equation given as here, del squared v equal to 0. So now this case is using cylindrical coordinate system. So referring to the table, if we get to the table given, for the case of cylindrical, del squared v is equal to 1 over r d over dr r dv over dr plus 1 over r squared d squared v over dv squared plus d squared v over dz squared. Okay, guys. So we know clearly from the diagrams the potential depending on the radius, isn't it? So at R equal to A, 100 volt, and again when R equal to B, 0 volt, it means that there's no effect on these two terms. So we can simply ignore the phi term and also the z term, just focusing on the R term. This equation we can just equal to 0 because we assume it's a free charge medium. So let's solve together. So how to find the V equation? So here you can have 1 over R, d over dr, r dv, or dr is equal to 0. So now, so let's do integration for both sides. So before that, let's put dr to decide what happened. The r times 0 got 0, so the r is gone. So let's do first integrations. So I'm gone already. So first integration, you're going to have here the r dv dr equal to a, isn't it? Because integration of 0, we got a is constant. So now put the r here down there. So you're going to have here d over dr equal to a over r, agree? And now we do the second integration for both sides, here and here. So now you have here a v become a ln r plus b, isn't it? So integration 1 over r got ln r and plus a constant there. So that's your the general equation for the v potential. And now let's solve this equation by putting or substituting all the value given the equations from the boundary conditions, whereby we know that at r equal to a, the v is 100, and r equal to b, the v is 0, right? Now let's put inside the equation. The first one, r equal to b, so the v becomes 0, so a ln b plus b. Okay, for this case, when r equal to b, the v comes to 0. So put there. So I have this equation. So can I have b? Yes, the b will have as negative a ln b. That's your b, right? Second conditions of the boundary, whereby we know that at r equal to a, the v is equal to 100. So put here hundreds equal to the a ln a plus b again. So now you can just taking the b is equal to 100 minus a ln a. Agree? Okay, now we have two equations now. The first is here, first and second. So the b is same. So let's equal them. So you're gonna have, if put 1 is equal to 2. So you see here 100 minus a ln a equal to minus a ln b. Let's combine this ln and this ln. So put over there. So you have here hundreds equal to a ln, no, b, sorry, ln a plus a ln a, isn't it? So put this a ln a to the right hand side. So you have a become positive. So let's simplify. You have here a ln a over b. Agree? Because ln a minus ln b become a over b. So there's hundreds. So you can have here a finally become hundreds over ln a over b. Agree? So that's your a value. So now help me to find the b value. So, sorry. So the b can be obtained using either one, either from first or second equation. Let's say I want to take the b from here. B is equal to minus a ln b. Okay? B equal to minus a ln b. So what a guys, a is obtained previously. That's your a value, 100 over ln a over b. So why by this one is hundreds over ln a over b. So put inside this equation value to these equations. So you're gonna have the v value finally negative hundreds ln a over v times ln b. So that's the result of this. So how do we actually simplify the equation? So you can put everything back to the equation of v from previously. one, D equal to A ln R plus B. So V equal to the A ln R plus B. So put the A and the B as well. So here we're going to have here 100 over ln A plus B now become ln R minus 100 ln A plus B ln B. Right, so let's simplify. So factorize the equation. We're going to have here 100 ln A over B. Now here ln R over. So that's your equation for potential. Right, you see? So that's the V equations. In terms of R, it means that the potential difference varies by R. When the R go to 5 mm, the V become 100. When the R become 15 mm, the V becomes 0. So that's equation. So if you want to get the specific value, so just plug in the value of A and B. Then you can get the value of potential or equation of potential. So now the same thing, if you want to proceed to find the E, just using these equations, the E is equal to a negative grad V. So just refer to the table for the case of cylindrical. So the grad of V for the case of cylindrical given as grad of V, case of cylindrical, you can see from table, the R component dV over dr plus phi component over R, then dV over d phi plus z component dV over dz. And we know that again, the V for this case only depend on R radius. So it means that we can ignore this phi term, also the z term. So just finding the E using the first term here. So the V, the E here, actually a negative R component. So the D over dr, and put all this equation value inside this one. So this guys, this whole term is your constant. So you just ignore. So 100 over ln A over B ln R over B. Right? So this whole term is your constant. So take it out. So you can have here negative 100 R component over ln A plus B. So here actually a D over dr. So now here guys, we can actually decompose into two, become ln R minus ln B. Agree? So now let's look at this one. What happens if you integrate this to the R? Well, this is constant, right? So this one will have 0 because the R on ln B becomes 0 because B is constant. So we just only have this term, right? So what should be the answer for this case? We have here negative 100 R component over ln A over B. So what should be the output for this differentiation? So we're going to have here 1 over R. Agree? So that's the value of E, the equation of E. So we can simplify the equation, become this form, a negative 100 R component over R ln A over B, so the V parameter. So that's equation for the E field. The E field here is equal to these equations. This is how we get the E. So again, if you want to proceed to find the D, simple, just put or plug in the epsilon r, epsilon naught. It's shown here to find the D, become epsilon E. So this case, the epsilon given as 2.0. So just put here a negative 200 epsilon naught R component over the R ln A over B. And now this case become Coulomb per meter squared. And bear in mind the D and the E always have same direction because this is a case of isotropic. So R, so the R here. So that's how we get the D equation. This is how we get the E equation. And this is how we get the V equations. Yes, thank you. So that's how we solve the case of cylindrical capacitor. Okay, now let's proceed to the last example using case of spherical. So let's right. Okay, now. Okay.